excellent talk from Sungjin, who has done lots of great papers on the space of spatial learning, object-centric, and so forth. And today we're gonna have him present his recent work on neural language of thought models. Thank you very much.
Yeah, thank you for the introduction, Curtis. Yeah, nice to meeting you guys. It's actually my first time attending CVP. I've been mostly attending only the machine learning conferences, so it's very exciting for me to present this talk. This is also about like object-centric learning, but I have a slightly different view in this talk. So I try to provide some view from combining some view from cognitive science and also some neuroscience through this theory of language of thought models. So yeah, generative AI has been like very hot and making really impressive progresses in the past. So we are expecting a lot of things like soon we will have like a Jarvis like AI. Yeah, different people have different expectations, but I think it's important for us to understand where are we now. There is no very common consensus. Everyone has their subjective perspectives, but these are something, the strengths and weaknesses of the AI nowadays. The strengths is it has pretty good perception for vision and language and so on, speech, and it can generate good content, very high resolution controlled by human language, fluent conversation, and it can help programmers to some extent, and it has a lot of breadth of knowledge, like it's a conversational search engine. But it also has weaknesses still, so computational generalization, there are many papers, it has limitations in that area. And also for some problems, it needs to do infer some latent algorithms, but it cannot do it pretty well, not well. And mathematical reasoning, long-range planning, causal understanding. And also important, it can't do much high-level things without language. If you think about it, everything, the fancy functionalities are in connection to the language. So if you think about without language, what we can do is pretty much generating samples. Yeah, it's very high quality, but not much high-level cognitive abilities are there. So some failure cases, yeah, there are many failure cases, but I'm bringing just one case here from ChatGPT 4.0. Yeah, it actual instances. So on the right-hand side, some people show this heptagon picture and ask how many sides does this structure have? And it first says 10 sides, and the user said that that's wrong, and then it said, I apologize for the mistake, and it has 9 sides. Are you sure about that? Asked, and it said it now has, oh, now I'm sure it has 8 sides. So it seems like it's not really, and for humans, the process going inside our brain is maybe, okay, let us count the number of like the lines, and then, okay, 7 lines, and then, okay, 7 lines is usually called heptagon, so we say heptagon, but somewhat different processes going behind. Where are we heading toward? We don't know yet what's the clear and fundamental solution for the weaknesses yet. There are some scale maximalists who says like bigger transformers, more data, more modalities would solve the problem for someday. That's important accesses, but maybe not enough. So maybe we are missing something else. So I want to reflect where are we and where should we go through the lens of 2 giants. Daniel Kahneman, who is a cognitive scientist, and Jerry Fodor, who is a philosopher, actually the expert of mind. So Daniel Kahneman has this famous theory, the dual process theory of system 1 and 2. So system 1 is like something what we can intuitively know. Like for example, if I give this example of 3 + 7, you know the answer exactly, right? But systems on the right-hand side, like if I give 3 × 7, you do not have the answer immediately. Some of you may have it if you have like, if you pose that question a lot, but most of the people require thinking, some kind of sequential thinking processes. So the system 1 and 2 theory says we have these two different processes in our brain. And another very useful framework is this knowing and thinking framework. So maybe we have these two different ways of understanding or solving some cognitive problems. So system one is very similar to knowing. If you are exposed a lot of times for similar problems, you actually encode that experience in your brain as a knowledge. So you immediately know the answer. That's like solving some unfamiliar problems, but you can still solve it by unfolding some sequential knowledge manipulation processes. You have some building blocks in your brain, and then you need to manipulate this to get the answer. So it's just a very useful framework to understand what's following. So the question is, do current LLMs provide system two abilities? So these are the strengths and weaknesses I showed in the previous slide. And I think the strengths part, it seems like it's just somewhere between system one and system two. So very strong system two problems, it's just still not solving it. But some part, like someone can ask, isn't it like a system two, like a helping programming? But if we look into how it is doing, actually, there are many failure cases. And my understanding or my perspective is like, it seems like current LLMs seems to be tackling the thinking problem. For example, the programming is a very sequential reasoning problem that requires thinking, but the LLMs has exposed a lot of examples. So it has also a lot of like experience. So it tries to solve this problem by knowing abilities. So it makes some kind of hallucination that we can see in many places, like the heptagon examples as well. So instead of like discretely splitting the system one and system two, we could think of it like as a spectrum between system one and two. And currently, we may be somewhere in between, not yet like achieving the strong system two abilities, but somewhat like going close to like a weakly system two abilities we are achieving. And this limitation actually very well matches some neuroscientific evidences. So do language fluency mean system two fluency? So neuroscience says no. So there are like many evidences. First, anatomically, these two abilities are processed in very different areas. So mostly system two reasoning is in prefrontal cortex area, and linguistic fluency is like this Broca Wernicke area handles that. And there's this global aphasia patient, very interesting, who has some damage in this Broca Wernicke area and who lose almost all linguistic abilities, but these people can still play chess very well, can solve mathematical problems, can compose music. So these are also evidences this very high level reasoning ability, manipulating knowledge is somewhat not the same as the linguistic fluency. Also, fMRI study shows different areas being activated, and also from developmental cognitive science by Sperke et al. Shows that infants actually develop this kind of system to learn knowledge before acquiring language. So it seems like not a good, and it's from this natural science, neuroscience perspective, to see these linguistic fluency, the semantic abilities. So this is just visualization of what I told in the previous slide. So this purple area is Broca Wernicke area, which is like this language models. So it's more, I see this area is handles something like LLM, which is not like a fine-tuned for instruction following. So, and this green area, the prefrontal cortex controls like word models and like some sequential knowledge processing. So either of these is damaged, then they show some interesting behavior. If prefrontal cortex is damaged, they can still speak something grammatically correct, a fluent language, but they show something like hallucination, what LLMs is doing, like saying something that doesn't match to the word model or common sense. The other way around, if someone has this damage in frontal cortex, but has damage in this Broca Berenice area, they have this problem. They can still play chess, solve some math problems. And this is another perspective of this table. So I kind of try to add another axis from system 2, 1, and 2. So one axis is linguistic, and the other axis is non-linguistic. So for both abilities, I think from system 1's perspective, I think we are doing pretty good. And from linguistic perspective, some part of system 2 abilities, like some helping programmers, are like generating some programs and solving some simple math problems are done in LLMs. So, but I think it's being solved by this knowing process instead of the thinking process. So I put here the triangle. And non-linguistic system 2 abilities, I think don't know pretty much how to do that, how to get the representation, how to do this knowledge manipulation. And I think what we are doing, object-centered learning or causal representation learning, is very much related to this area. And this limitation of LLMs, which cannot do the current approach, do this like high-level sequential knowledge manipulation. This actually was predicted 35 years ago by Jerry Fodor. He has written with Zenon Felicien in 1988 this very famous paper, Connectionism and Cognitive Architectures, a critical analysis. It basically says the purely distributed representation cannot systematically generalize. So it needs something called language of thought. So modern deep learning still, as far as I know, doesn't solve this problem yet. And I think this may be the reason why we see these hallucination problems. So looking a little bit more into this language of thought hypothesis, it's talking about in like expert system, like some 30, 40 years ago. This is still neural representation, but has this kind of sequential process. And also talking about systematic compositionality. So this means the meaning of mental sentences or the whole is determined by the meanings of the constituent parts, words, and their language. And by the way, this language of thought, the language doesn't mean the real language. It's just some representation which has some discrete entities, which we call symbols, and some kind of this representation that plays the role of grammar. And traditionally, also the neural network side, like we have different perspectives, different perspectives. The pure connectionist people, the eliminated connectionism people, they say we don't need this kind of sequential process or symbols or rules. So everything can be written in distributed way, and that basically eliminates this the need for Turing-like computation process. The current it's not binary. It's again kind of spectrum, but I think current deep learning, like for example, having single vector representing everything as like a firing of activations, is close to pure connectionist, but it's changing. Like we now have attention mechanisms and also tokens in LLMs. So that is moving us to more like implementation connectionist perspective, which says no, this really representation can be used to learn and express these symbols and rules. So yeah, I think we may need deep learning for language of thought to achieve system two abilities in more general. And this matches well also with recent neuroscientific studies, like this very famous paper by Stanislas Dehaene, Symbols and Mental Programs, a hypothesis about human singularity. I suggest this paper if you're interested in this area. And this brings us some research questions from AI or machine learning computer vision perspective, how to learn and represent symbols, rules, and how to execute, manipulate them. And yeah, I should speed up a little bit. Yeah, and I think instead of starting from language, I like to study this program from more unstructured modality like vision. The reason are here. Yeah, not all knowledge or intelligence can be described from language, and basically by learning from language, we are learning to imitate human knowledge, but I want to discover something more fundamental, just copying human knowledge, the basic real principle and mechanisms of human intelligence. And also Yang Lekon has been saying similar thing, before we get to human level AI, we will get to cat level AI and dog level AI and so on. So this is some overview summary of the figure. We interact with the world. We have system 1, system 2. I think language of thought hypothesis may be saying about how to implement the system 2. And I'm not sure where RMs you put in this figure, where currently I would put it somewhere in between like system 1 and 2, but not very inside system 2 because of these limitations. And here, just representing symbols and rules are an important aspect. And also, this system 2, 1 from cognitive science and from the philosophy of mind, the language of thought hypothesis, and studies from neuroscience from prefrontal cortex, working memory, and hippocampus. These are saying very similar things about like this symbol like manipulation processes. And I think from AI community, we also may need to provide some consistent story that may be neural language of some others. Yeah, that's pretty long overview and a little bit of technical part. I think traditionally we have this single all-in monolithic vector like a V or clip, and it's known that it's not generalizing well to multi-object scenes. So left-hand side is VA learning single object scenes. You can factorize and start learn this independent factors pretty well, but it doesn't generalize to multi-object. And also from the clip paper, we can see this phrase because it doesn't bind the attribute like position, color, shape, and so on into the representation in a separate independent way. It mixes up these attributes and object. And if you try to generate multiple samples from this representation, it actually doesn't preserve the right structure. And this is also a famous problem of this purely distributed representation called the superposition catastrophe, known more than 30 years ago. And the right way maybe is to have this multi-cell representation, which object-centered learning does. And yeah, this multi-cell representation, we are using slot attention a lot these days. It provides like object level compositionality. And yeah, here we treat basically object as a symbol, and that is some independent separate vectors. And it could be, or there are some works as well, it could be pretty useful for representing causal mechanisms, where some object plays a node in causal graph. And we have worked on some models like Slate and Steve, where we make use of very powerful decoder-like transformer, and it turned out that is very crucial to make it work for very complex images like this. This is very simple image, like just amnest with different textures behind and foreground and background, but it actually is very difficult task, and I'm very happy that our model can like figure out the foreground digits from these images. And it works now for this kind of images, videos, identifying the object, supervisory, working on some like a natural images. And also we have worked on this object-centric reinforcement learning for robotic control, and it turned out that this object-centric representation is really useful for improving the performance. So it actually identifies different objects, and then also the arms of the robot, and it models the interaction between these objects. And so, yeah, recently we have this model proposed this on neural systemic binder and neural knowledge language of thought models. So traditional slow representation excuse me, has this thing like we have a scene here, image, three objects with different properties. We usually represent it through like a three slots, and within slot it represent the factors or features in an encoded way, such as the shape, color, and so on. So we can imagine like this kind of representation where slot contains some factor representation, which we call blocks. And so each slot is composed of like multiple blocks. So some block play is the role of shape, and some other block provide the information about colors. So these are also factorized, and ideally we want it to provide some conceptual level as independent factors. And yeah, the question is how we can make it work. So to do this, we propose this blocks representation, and we want to implement this three decidera in this model. First one is within slot factor decomposition. The second thing is we want to represent the block as a vector instead of a single variable like V. And the third one is we want to implement this as like some neural architecture mechanism instead of adding some object loss like the KL independence regularization in VA. So to do this, we need to implement this principle of computationality in neural architecture. The first one is systematicity, which means the meaning of the whole is indicated by the meaning of the part. And productivity is telling the ability to generate or understand infinitely diverse observations by understanding the composition structure. You can think of like a language. Human natural language can generate, like we can understand infinitely diverse types of sentences. So the question is how to implement these inductive biases as in neural mechanisms. So neural systematic binder, this is our architecture. Looks pretty complex, but I'm gonna go through step by step. So given the image, we first deploy the slow attention encoder, which brings each object. So this figure is showing the process of handling just one object, but every object are handled in parallel. And then the second, we break the slots into some like in this case 3 blocks, and then each block is independently updated, some using GLU, and then that GLU actually, after updating its state, actually map its state to this concept library. You can think of this concept library as like a embeddings of word dictionaries. So it's like try to explain the GLU state, try to map it to some concept in this global concept library. And then we do gather these blocks together again, and then repeat this process a little bit, a few times, and then the final block slot is read out for reconstruction. This is like implementing the idea of like a part should explain the whole, or the whole should be explained by the meaning of part, the systematicity. And that process goes in parallel for multiple objects. This is just another view. And then as an output of a image encoder, which we call block slot encoder, we have this tokens, something very similar to language, but we have now shapes, colors, and position, and so on. So this is like a visual language, and we put it into transformer decoder, and it actually reconstructs the image using this. And from productivity wise, we have this language of thought prior. Now we connect this visual world very much like just GPT to some transformer or regressive model. And now it learns how to basically the implicit grammar of how scene should look like. For example, it would learn like we cannot have two shapes for one object, or we cannot have like two sizes for one object. So that kind of regular structure will be learned here. And then finally, by using this language of thought prior, we can generate like plausible realistic scenes, much like we generate sentences. Yeah, I'm going to skip some slides. And this is some experiment result. So after doing this, this is totally unsupervised process. When I say shape, color, we don't specify anything. The model automatically learns to find this concept, and we can see by visualizing the representation, it actually find the concept one. First concept library captures like materials, as you can see here, and positions and shapes and so on. So it learns how to what's the meaningful concept, which pretty much matches to human semantics of an object, even if it doesn't need to be. And we see their compositional abilities. So it's pretty interesting here. By doing this, we can now control the concept, like seeing this image as an input, because it has this interpretable like block concept. We can switch the concept. For example, in this case, just change the color, and then it can now generate very much the same image, but only that factor is switch it. You may be very familiar with this kind of abilities, because when we leverage language, but actually when we don't have language, this kind of controllability is not much available, I think, in my opinion, in machine learning computer vision communities. And yeah, pretty much the object-centered approach is so far modeling the static concepts like shape, color, and the segmentation of an object. But I think you should be able to capture also the dynamic abstract concepts, like the concept fast or slow, or moving right, left, or even more abstract concept like a number or loop. Like the question is, can we learn that kind of abilities? And to do that, we introduced this recurrent block slot units on RNN. There is basically like a set of slot RNNs, but what the difference is, every state update, after every state update, we squash their representation into this block slot concept space. So it means the RNN, if it is thinking process, it try to match this blurry representation into some concept. Okay, this is like a red color and so on. And also we found that to learn this dynamic concept, we should not reconstruct the current image. It should do predicted future prediction. Otherwise, we cannot capture this abstract concept like a fast, slow, and so on. So yeah, so we similar in the previous work, we found that this model can actually find and learn this dynamic concepts like moving direction and moving speed and so on. And yeah, in this experiment, actually, we can do this temporal compositional imagination experiment, meaning we can pick some concept like cyan circle moving down and mix this concept with existing concept, maybe changing the color with existing concept here, switching the concept to cyan. And this triplet, cyan, square, moving left, has never been in the training set. And we show that the model can still play that video. It can simulate it. So it's like I'm thinking this is the ability human can imagine some all these situations like flying Superman dog outside of this building. We have never seen it, but by composing some concept, we can do that. We can do this with language. This is trivial, but this is done without using any language. And finally, yeah, this is also some work to be published soon in our archive. So we have this slot state space model for efficient manipulation of temporal symbols. The concept is pretty simple. So we have transformers and SSM with the just monolithic state. Here we have like SSM with multiple slots as a independent slots as a state. If you know there's a recurrent independent mechanisms, this is pretty much similar, but brings all the benefits of slot SSM. Yeah, the idea is pretty much simple, but it performs really well compared to transformers and rings and so on. So this is multi-object video prediction. The second thing is ours, and this all red is errors, and the orange is the hits. And this is the error. Ours is answers is good as the transformer, slow transformer, which is like the upper bound in terms of the performance, but computationally, transformer is much slower than ours. And yeah, this is also very effective for long context reasoning, and also pretty good performance for object-centered running, and very good performance also for visual reasoning tasks. Okay, so the conclusion is I've been trying to provide my perspective of object-centered learning and maybe somewhat related to causal learning from the perspective of system 1 and 2 and language of thought hypothesis. And think deep learning we need for neural language of thought models. And I introduced some models to do this, and I think this could be a very useful block for causality and robotics. And for future, we need some more work on grammars and scaling this process.
Yeah, thank you very much for this wonderful talk.
Blocks with color, size. How do those blocks get trained? How do they specifically one lambda color and one lambda shape?
Yeah, yeah, basically it's similar to maybe VA. So VA eventually learns this in some of the individual variables to capture maybe position and colors. In that case, they use the scale independence regularization, but here we have this separated concept library, and each block can take the value from each corresponding concept library, and another block can only take its value from each corresponding temporal block. So and then we implicitly split these two, and then they are updated through independent GLUs. So they are somehow being updating each state independently, not knowing each other. But eventually they should be merged again and should reconstruct the image. Then these blocks should try to separate each role. Okay, someone should take care of shape, somebody should take care of color and so on. So that role is determined by this reconstruction loss and through the learning. So this is emergent and maybe more like an art of like a designing the architecture, because we don't use any specific loss function to encourage this. So like attention mechanism shows this attention pattern. So yeah, so yeah.